a lot of structural and mechanical uses for pipe. You see, a tubular than any other shape. It is used vertically and horizontally to convey gases and liquids, as casing and tubing down in a hole, or as line pipe to transport gases and oils. Each application has its own problems. Each joint has its own definite specifications. Maybe you need long length, maybe not. Maybe you're going to weld it and bend it in the field. Maybe you need ductility or a high yield point. Maybe you need both. Maybe it's a problem of stress factors from pressure, or maybe it's temperature and pressure. Whatever it is, you have to know exactly what you want before steel pipe is made. The end use of the pipe will determine its characteristics. In making oil country goods, the American Petroleum Institute sets up the specifications, and the pipe is made to those rigid API standards. In order to understand the story completely, let's start at the beginning. We start with the raw materials: coal, limestone, and iron ore. The first thing is to change the coal into coke. There's a battery of coke ovens. You see, coke is almost all carbon and is useful not only as a fuel, but as an important chemical element in reducing iron ore. The next step is charging the blast furnace. We charge the raw materials, ore, limestone, and coke, in at the top and blast hot air up from the bottom. The hottest part is in the hearth at the bottom. The melted limestone combines with the undesirable elements and is drawn off separately as slag. The molten iron can be cast into pigs or taken right over and refined into steel. Here's the open hearth, where iron is refined into steel. Limestone and scrap are charged. Then the hot metal, which was made in the blast furnace, is added, and the charge is melted down with a giant flame. It gets hot all right, up toward 3,000 degrees. And when everything is just right, the molten steel is tapped out of the furnace into the ladle. Just right means okay chemically and okay according to the melter's experienced judgment. Take a look at that ladle. Holds about 150 tons. Look what it takes to support it. And think of hanging that much weight from a joint of pipe, all that suspended in tension from the threads. It makes you stop and think of how much we ask of a joint of pipe. But more of that later. After the tapping is completed, the steel is poured into molds. The ingots cool down enough to get solid, and the next step is to get them ready for rolling. You can't do a good job unless the temperature, inside and out, is exactly uniform. So the ingots are heated carefully in what are called soaking pits. The ingot is rolled in a blooming mill. It's like a giant wringer. The ingot passes back and forth under tremendous pressure. Two things happen. The physical properties of the metal are improved, and it's rolled into the desired shape. We can roll it into slabs, which can later be processed into scalp for electric weld pipe, or roll it into blooms, which can later be processed into tube rounds for seamless pipe. Regardless of which way we decide to make the pipe, a number of processing steps must be taken. To better understand the steps in producing pipe, let's take a look at a flow chart showing both methods. Here we see what we've done so far. From the ingot, we can start making pipe by the seamless method or by the electric weld process. To make a length of J55 to API standards, we start with the same basic steel operations and then simply handle it one way or the other. If we want to make it by the seamless method, we follow these steps. If, however, we want to make it by the electric resistance welding process, we follow these steps. In either case, the result is the same, an API-approved length of J55, tested and ready to do a job in the field. How do we know this? Each length of pipe, no matter how it was produced, undergoes the same rigid testing. When a buyer orders a length of J55, he can be sure that this pipe, whether it's seamless or electric weld, will have a minimum of 55,000 pounds per square inch yield strength. Now let's see each type of pipe being produced. For seamless pipe, the ingot is rolled into a bloom, which will later be processed into rounds. We call them tube rounds. Then the round, which has been cut to length to produce the size and weight of pipe desired, enters the rotary hearth furnace, is heated to the right temperature for piercing, and hot centered. You can see it now, moving along the conveyor on the way to the number 1 piercer. A ram pushes the round into the piercer rolls. At the same time, a mandrel bar advances from the opposite side of the rolls and engages the piercer point, holding it ready and in position for the round to be forced over it and made into a tube hollow. Here this action is shown in simplified drawings. The round is forced over the piercer point and mandrel bar by the action of the barrel rolls. Note that the steel is elongated over the piercer point. No slug of steel is punched out. Any steel that will stand this operation has to be good. Then the pierced hollow is rolled out onto the outlet table and transferred to another piercing operation, like the first, to reduce the wall thickness and lengthen the pierced hollow. A quick glance at the flow chart shows us that we now have an elongated pierced hollow. However, in order to have a length of seamless pipe that meets API specifications, this hollow must undergo several more operations. After the piercing operation, the tube is passed over a blunt-shaped plug in the high mill, which substantially lengthens the pierced hollow, reduces its wall thickness, and slightly reduces its diameter. A second pass is usually made using a slightly larger plug to ensure a uniform wall. After this operation, the original short tube round has been increased in length to the approximate finished length of the pipe. Reeler rolls help to finish the pipe. They do the work on the outside, while a mandrel bar holds a reeler plug to finish the inside surface. Now we're getting someplace. In this big hot sizing mill, the hollow is reduced to its final dimensions and is ready to be called seamless pipe. Here's an additional operation on N80 pipe. It's heat treated to develop the required physical properties. But let's get back to J55. Here's some 5.5-inch casing. This bypasses the heat treating furnace and goes to the straightening rolls. Then it's inspected for exterior and interior surface quality. Here's the cut-off machine where the crop ends are removed. An inspector gauges the wall thickness and the pipe is sent on for finishing. Then our seamless pipe is threaded accurately in an automatic machine. He's checking the threads with the size gauge. This is only one of the many ways we inspect the threads to determine conformance with API standards. Couplings are put on to the hand-tight position and then made power-tight and moved along. One by one, each joint is hydrostatically tested, inspected again, coated and stenciled, and then it's ready to go. There you have it, seamless pipe. What you've seen here were just the manufacturing highlights. A little later, you'll see more of the inspection, tests, and controls. But right now, let's go back and see how J55 is made by the electric weld process. We said that from the ingot, pipe can be made by either the seamless method or electric resistance welding. Let's follow the production of pipe by the electric weld method. Instead of making tube rounds, let's roll out some slabs for pipe scalp. Here's a big modern strip mill. You can see the scalp coming from the finishing stands. The pipe walls will be as uniform as the flat-rolled scalp, a readily controllable dimension. The way we trim it, both sides at the same time, gives uniform width for the full length of the scalp and makes uniform edges for welding. The surfaces that will make contact with the electrode are shot blasted to ensure ideal welding conditions, and then it goes to the forming rolls. There are a number of stages, and the flat scalp is formed progressively into an open tube. Electric resistance welding was pioneered by Republic in 1928, and we've been producing it for over a quarter of a century. With all this experience, we've developed a precise control over time, temperature, and pressure that must be achieved to produce a uniform weld that is as strong as the parent metal. What is done is this: raise the edges to a welding temperature and then force them together under pressure. No metal is added. The weld is formed entirely of the parent metal. It's all automatic. Everything is controlled to give both a fine ductile condition with the least variation in the grain structure. Here's a diagram of it. There are 3 pressure rolls, all turning with the electrode. The open tube moves right into the welding machine, where the revolving electrodes contact the steel close to each edge. Careful coordination of speed, pressure, and current by means of an elaborate system of controls produces a metallic bond from the parent metal. Just enough is extruded inside and outside to give a uniformly strong weld. Stationary cutters remove the extruded metal and leave the wall thickness at the weld, the same as at any other point. There you can see it. The metal is still plastic, and the stationary cutters are removing the extruded metal, leaving the wall thickness the same all the way around. A glance at the flow chart shows that we have now made a piece of electric weld pipe. We've finished the welding and the flash cutting steps. Now it's ready for the straightener. The pipe passes through a series of concave rolls and is made perfectly straight. The entire length is carefully checked by inspectors, and the ends are marked for cropping. A piece from both ends is put under a crusher and flattened according to the specifications for that grade. This is a double test of both the steel and the weld. Then, with oil country casing and tubing, we bring the metal to the proper temperature in a normalizing furnace, which produces a tube of uniform and refined grain structure with uniform hardness all the way around. The casing has purposely been formed and welded larger than desired finish size, so it is cold sized down to the correct OD. Cold reduction in size increases the yield strength and still maintains the ductility. This provides maximum resistance to collapse pressure. The uniformity of the wall leaves the maximum amount of metal under the thread roots, providing extra resistance to pull-outs. Then it goes to be threaded. Threading is a precision job, and nothing is left to chance. The threaded end is visually inspected and checked in several ways. Here's a spot check with a Zeiss microscope. Each length is put in a hydrostatic testing machine, welled up, and given the pressure specified for the grade, diameter, and wall thickness. Pneumatic hammers strike the pipe while it's still under pressure. After it passes, it goes on to a series of other tests. We check on OD tolerances, wall thickness, and look for surface defects, both inside and out. Now we've made some seamless pipe and we've made some electric weld pipe, both from the same starting point. And both are made to the same rigid API specifications that will stamp this pipe from either manufacturing process, J55, good for any job requiring a minimum yield of 55,000 pounds per square inch. So there you have it. Two pieces of pipe, ready for the same job. What is the difference? Are they alike physically? Let's go up to the laboratory. Here's a yield test on sections of seamless and electric weld pipe. The usefulness of pipe for an engineer isn't so much its ultimate strength, it's the yield point. All design formulas for pressure piping, for instance, are based on yield. The testing machine is applying stress to establish the yield point. The API established a standard of 55,000 pounds minimum yield on the J55 grade. Let's see. Yeah, this one makes it. Yeah, they're both above the minimum standard. Grade for grade and weight for weight, electric resistance weld pipe has the same minimum performance values as seamless, the same physical properties, collapse setting depth, the same tension setting depth. This is a fact that was recognized by the API many years ago. Remember that Republic makes both products, knows that both are rated equally in standard specifications such as API 5A, 5L, and 5LX. ASTM A120 and A53. Results can be changed by changing the ingredients. We can get strength by chemicals, higher carbons, more manganese, for instance. Or we can get it by the cold work, which is done on the steel during the forming and sizing operations. Keep in the back of your mind that electric weld pipe is made from flat skelp. We can see what will be the inside of the pipe, and we can see it before the pipe is formed. The way the scalp is produced makes a remarkably uniform wall, and this is important. Uniform wall thickness means that you have the same thickness under the roots of the thread, all the way around the circumference of the pipe. Add to this the speed and the controls of ideal welding conditions. The cold forming and cold sizing operations do two things. They build up the yield strength and eliminate all heavy scale. Electric weld pipe is consistently lower in carbon and manganese, so of course it's easier to weld. It has many advantages for the pipeline user in particular. Free from scale and defects, it's easy to bend, and the long straight lengths cut installation and maintenance costs. Here's a crew running casing. They've just switched from N80 seamless to J55 electric weld, both made by the same company and both used the same way. It's just a matter of setting depths, pressures, and specifications, and it's not a matter of bias or prejudice. Now, one more thing. This shot was made 2 miles from the rig, quite a distance, but that's the length of pipe hanging below that platform. Now, let me show you what I think is right there with that. It's people. A lot of people over a long period of time. People mine the iron ore, the coal, and the limestone, the raw materials. People feed the blast furnaces, the open hearth. People who run the pipe mills. People check and test and inspect each piece of pipe all the way through to the shipping platform. People who've pioneered the finest facilities and controls for electric resistance welding, and people with the finest facilities for making seamless. People who make both. People working together in a fully integrated company, but people who know what, know why, and know how.